All right, hi folks. This is Larry Maslino. I'm recording a video for Module 10 in Math 181, and I want to give you a little background, help you get started in the WebAssign homework. Now, there's going to be a couple of key formulas in this module. So I'm coming here to the lecture notes that are posted in Canvas, and let me come down here and give you a little background on this idea of conditional probability. So a conditional probability is asking you to calculate a probability on the condition that another event has occurred. Here's an example. Maybe a medical researcher wants to know the probability that a patient fully recovers from heart surgery, given that the patient is diabetic. So when calculating that probability, we're only looking at diabetic patients only, because that's the given condition. I would not be examining data for non-diabetic patients, right? So notice here it says the medical researcher wants to focus only on diabetic patients to come up with this probability. So what you're going to see is this notation. It's going to be the probability of A with a vertical bar. And you got to be careful. This vertical bar does not mean division. When you see this notation, this vertical bar is telling you, given the condition B has already occurred. So really, when you see this notation, it's asking you find the probability for event A, assuming that event B has already taken place. Okay, so let's go and do an example here below about a person getting the flu. Okay, let's do that. So in this example, it says we want to know the probability that a person gets the flu given that they're over 65. So again, the word given, I'm going to translate into a vertical bar. So here it is. I want to know the probability that someone gets the flu given that they're over 65. Well, here is a formula we're going to use. If you want to know the probability of A given B, the way you calculate this is set up a fraction. I want to know the probability of A and B happening together divided by the probability of B. All right, well, in our example, event A is the flu, and event B is that someone is over 65. So that means I really want to know the probability that someone gets the flu and they're over 65 divided by the probability that they're over 65. Well, let's see what they're telling us here. We know 20% of the population is over 65. Well, that's telling me the denominator here is 0.20. And let's assume the probability that someone gets the flu and they're over 65 is 12%. Well, that's this and probability that we're looking for on the top. So this is going to be 0.12 on the top. And if I work this out, this is 0.6. So the probability that someone gets the flu, given that they're over 65, is about 60%. Okay. So this is going to be an important formula that we use. And notice sometimes you see it written as the probability of A intersection B. This upside down U is the intersection symbol. So when you see this intersection symbol, think of the word and. Okay. All right. Now, one other thing you could do with this formula is you can rearrange it to make it a little bit more convenient, depending on what you want to know. So here is the formula we just mentioned. The probability of A given B is the probability of A and B divided by the probability of B. Well, sometimes I might want to know the probability of A and B where I know the conditional probability. Well, I'm just going to do a little algebra, and I'm going to multiply both sides of this equation by the probability of B. Well, on the right-hand side, this denominator cancels out with the numerator there. And so I end up with this formula here that you see. So we could say the probability of A and B is going to be equal to this left side, which is the conditional probability of A given B, times the probability B. Okay, so this formula A is really the same as this formula B. It's just rewritten using a little bit of algebra. So you can use either one of those formulas to solve some of these examples. All right, so let's go into WebAssign and do some examples. Before I do that, let me just scroll down a little bit. Please read through these examples. Folks, these will be very helpful examples as you go into WebAssign, because some of the WebAssign problems will be very similar to this. Let me mention, and of course, watch this video, please, on conditional probability. Let me mention one other item here on independence. So here is a discussion about independence. Well, maybe events A and B are totally unrelated. That means the probability of one event happening is in no way affected by the probability of B. Let me give you an example. Let's say A is flipping a coin and getting heads. That's event A. And let's say event B is rolling a die and getting an even number. Well, these two events are in no way related, right? What happens with flipping the coin is in no way affected by rolling the die. So we would say these events are independent. When that happens, we can simplify the formula a little bit, because if you remember, the probability of A and B is equal to the probability of A given B times the probability of B. But this conditional probability really is the same as the probability of A, because if you think about it, I want to know the probability of A given that event B has happened. Well, I don't really care about event B, because event A is not related in any way. So it really doesn't matter to me if event B has occurred or not occurred. That's not going to affect the probability for event A, because these events are known to be independent. So the simplified formula, when you know the events are independent, is this formula here. So this is the formula to use if A and B are independent. So you'll have to read a problem carefully and ask yourself, are these events A and B independent, or are they dependent? Dependent would mean if event B happens, it does affect the probability for event A. Okay, so why don't we go and do some examples from WebAssign. Let me bring up the WebAssign homework and we'll try to do a few examples here. Okay. All right, let's go to this first example. And, you know, it's always a good idea to write down all of the information they're giving you, and then you could try to fill in a formula that might be applicable. So I noticed they're giving me the probability of B. They're giving me the probability of A and B. And they're asking me to find the probability of A given B. Remember, this is called a conditional probability. All right, well, I could go ahead and use the formula that we've just been talking about. The formula looks like this. The probability of, I'm gonna write it like this just to be consistent. So I'm gonna write it like this. Okay, by the way, this is on page 530 in the textbook. And folks, please look at the textbook. There's a lot of worked out examples in the textbook. And you might know this, but WebAssign gets its homework problems from the textbook. So if you can look at the example, the worked out example in the textbook, that's going to be a very good background for these WebAssign homework problems. Well, now I'm just going to plug in the info that I'm given. They told me that this probability is 0.3. The probability of A given B is unknown. And they told me that the probability of B was 0.5. Well, I could just multiply both sides by 0.5 now. because that'll cancel this out. So I end up that the probability of A given B is 0.5 times 0.3. And of course, that's just 0.15. Okay, so this was just a simple substitution into the formula. Let me go to problem 2. I think you'll see problem 2 is similar. Again, I'm going to go to this formula that says the probability of A and B is the probability of A given B over the probability of B. Well, for this problem, they're giving me the probability of A given B, that's 0.1, so that's going to go on the top of the fraction. They're giving me the probability of B is 0.7, that's going to go on the bottom of the fraction. Now I just have to work this out on my calculator. 0.1 divided by 0.7 is, now let's see here, they're not giving me, I'm sorry, folks, I wrote this formula incorrect. Whoops, my mistake here. Let me back up. I copied down the formula incorrectly. It should be the problem. I was thinking of the other version of the formula as I was writing this, so my apologies. Let me back up here. Let's go back to problem 1 again. I should have been writing this formula as the probability of A given B is the probability of A intersection B over the probability of B, right? So again, this is on page 530. I guess I should have looked at the textbook myself before setting this in. All right, well, then in this case, for part A, they're giving me the probability of A intersection B, that's 0.3. And they're giving me the probability of B, that's 0.5. So I can work this out on my calculator, and I'm getting the answer here, 0.6. So this is the answer for number 1. Okay. All right, let's go down here to number 2. And I'm going to write down the correct version of the formula, of course. So the correct version of the formula is the probability of A given B equals probability of A and B over probability of B. Now I'm going to plug in what they're giving me. They're telling me the probability of A given B in this problem is 0.1. So that's going to be 0.1 equals, I don't know the probability of A and B. That's what they're asking me to find, but the probability of B is 0.7. Now I can just multiply both sides here by 0.7. That'll cancel that out. So we're ending up here, the probability of A and B is 0.07. Okay, so there'll be quite a few problems in WebAssign that really ask you to use this formula. And they'll give you 2 of the 3 quantities and ask you to figure out the 3rd quantity. All right, let's do a few more examples. Let me come down here to number 3. All right, so number 3, again, is asking me to use this formula that says the probability of A given B is probability of A and B divided by the probability of B. They're giving me the probability of A given B is 0.4. They're giving me the probability of A and B is 0.3, and they want me to figure out the probability of B. Well, for this kind of a problem, I'd like to get rid of fractions. So how about if I multiply both sides by the probability of B? Because if I do that, this denominator cancels out with that numerator, and I'm ending up at 0.4 times the probability of B is 0.3. Now I can just divide both sides by 0.4 to get the probability of B by itself, and 0.3 divided by 0.4 on my calculator is 0.75. All right, let me go to question 4. Question 4, they're giving me the probability of A, probability of B, and they're telling me that A and B are independent. Well, it's important that I recognize the fact that these events are independent, because that tells me to use a new formula. If you remember, the probability of A and B is just equal to the probability of A times the probability of B. But this formula only applies if A and B are independent. And of course, in this example, they are. So I can just, and remember, the probability of A and B is the same as the probability of the A intersection. Well, the probability of A was given as 0.6. Probability of B was given as 0.3. So this answer is just going to be multiplying those 2 probabilities together to get 0.18. Okay. All right. Let's do an example a little different. How about if we go to number 5? So number 5 is really asking you to interpret the wording of this problem. So let me clearly write down what the events are. So it looks like they're defining event L to be lawyers who lost clients. Okay. And then event A is the event that a lawyer is an antitrust lawyer. All right, let me go to this first sentence here. It says 50% of all lawyers who lost clients were antitrust lawyers. So really the way I can think about that is the probability that a lawyer is an antitrust lawyer, given that they lost clients, that probability is 0.5. So I'm just translating the first sentence, right? First sentence says the probability that a lawyer is an antitrust lawyer, given that they lost clients, that's 0.5. So in WebAssign, I would just be picking an L from this drop-down menu and entering 0.5 in this box. I'm not doing any calculations. I'm just translating the sentence. Let me go to the second sentence. I'll circle it in blue. The second sentence says 30% of all antitrust lawyers lost clients. Well, the way I can think about that is it's telling me the probability that a lawyer lost a client, given that they were an antitrust lawyer, is 0.3. So the second sentence is really flipping around the conditional probability. So the second sentence I can write as the probability of L given A equals 0.3. All right, let me scroll down and let's do something a little different. Let's come to number 8. That's a diagram kind of question. All right, well, there's two parts to this problem. Part 1, I have to fill in these boxes up here in the diagram. And then part 2 is I have to calculate these probabilities that they're asking me for. So let me go to the diagram. Well, anytime you have a branch like this, these probabilities have to add up to 1. Because if I'm starting at this origin, I'll call it, you have a choice of either going to node A or node B. Well, this is telling me there's a 20% chance of going to node A. That must mean you have an 80% chance of going to node B. So at each one of these branches, the probabilities have to add up to 1. So I'm going to put a 0.8 here because these probabilities have to add to 1. Let me come to this branch. Again, these probabilities have to add to 1. So I've got to put a 0.5 in this upper box so that those probabilities add up to 1. How about at this branch? Well, if there's 0.2 for the top branch, I need 0.8 on the bottom branch. All right, so I filled in the boxes. Now I can go to part 2 of the question. All right, let's do the first one. It says the probability of A and C. Remember, this intersection symbol means and. Well, the probability of A and C, let me just erase some of this here to make it a little easier to see. The probability of A and C means I'm traveling down this road, right? Because I want to know the probability of A and C. It must mean that I traveled in this red box. Well, that's really the probability of A, which is 0.2, times the probability of getting to C, which is 0.5. So all I have to do here is multiply the probabilities along the path I'm traveling. So this would be 0.1. Okay, let me do one more example. How about if I go to the bottom? The probability of B and D. Well, I just have to travel along that path. So to go to B and D means I'm traveling along this brown path. Well, that would mean 0.8 times 0.8, which is 0.64. So first step here is you got to fill in this diagram. To do that, make a note that the branches have to add up to 1. You know, 2 branches coming out of the same node, those probabilities must add up to 1. And then to do part 2 of this question, multiply the probabilities for the path you're taking depending on the nodes that the problem gives you. Okay. Let's go to number 10. All right, so number 10 is asking me, are these events independent, mutually exclusive, or neither? Well, of course, before I can answer this, I have to know what are the definitions of independent and mutually exclusive. Well, independent means the probability of one event is not affected by the probability of the other event. Right? It means the 2 events are totally unrelated. The example I used earlier was flipping a coin and rolling a die. What happens with one of those events has no effect at all on the other event. What about mutually exclusive? Well, mutually exclusive are 2 events that cannot occur together, cannot occur at the same time. Let me give you a couple of examples. How about if I'm picking a card out of a deck? And I ask, and let's say event A is picking a 7. Event B is picking a queen. Well, if I'm picking one card from the deck, I can't pick a 7 and a queen at the same time. That's impossible. So we would say these events are mutually exclusive, because these 2 events cannot happen together. Let me give you another example. What if event C was picking a heart and event D was picking a king? Well, these 2 events can happen together because I might happen to pick the card that's the king of hearts. Well, if I pick the king of hearts, both of these events happened at the same time. That means these events are not mutually exclusive. All right, so now let's go and see what they're talking about. They say event A is your skateboard design is a success. Event B, your skateboard design is a failure. Well, these 2 events can happen at the same time. Your skateboard design can't be a success and a failure at the same time. So these events cannot happen together. That means they are mutually exclusive. So mutually exclusive is the answer on that one. Okay. Why don't we do a couple of these word problems? Now, when you get to these word problems, really it's going to be a matter of translating into these probability quantities. And remember, the typical probability quantities we have are the probability of A given B or the probability of A and B. Because then I can usually use the formula that says the probability of A given B is the probability of A and B divided by the probability B. All right, so let's go to problem 12. So let's see here. It says, in a certain year, the probability that a person declares bankruptcy is 0.004. Okay. Then it says the probability that a person declares bankruptcy and, notice the word and had a big 3 event is 0.002. So I'm noticing they want to know what's the probability that a person had a big 3 event given that they declared bankruptcy. So they want to know what's the probability that someone had a big 3 event given that they declared bankruptcy. Well, I could see that this is going to be event A, big 3 event, and this is going to be event B, declaring bankruptcy. Well, according to our formula, I'm going to write this as the probability that someone has a big 3 event and declared bankruptcy over event B. Well, event B is the probability that they declare bankruptcy. Well, they really gave me these probabilities in the problem. This and probability was given as 0.002. The probability of bankruptcy was given in the problem as 0.004. So I can just work this out on my calculator. I think this just works out to be 0.5. All right, so I got to just be a little careful here to carefully interpret the probabilities that they're giving me in the problem, and then think about plugging into one of the formulas here from Module 10. Okay, let's do maybe a couple more. Let's go to 13. 13 is a little tricky because of the wording they're giving me. All right, let's see here what they're telling me. And again, I think it's a good idea to make a table up or somehow summarize the data. All right, here it says, during a year ending April 30, there were approximately 5 million sales of homes. So let me write that down. During the year ending April 30, there was a total of 5 million sales. Okay. Then it says there were 1.3 million sold in the West. So sold in the West was 1.3 million. Okay. Let me come to this other statement. It says during April only. Remember, this is a yearly data we just came up with, but now they're asking me to think about April. So during the month of April, let me write this as the month of April. They're telling me there was a total of 440,000 homes sold, and 140,000 of them were sold in the West. All right, so I think I know. I think I've labeled the data they're giving me. Let's go to the questions. Part A, find the probability that a home sale in the year April 30 took place in the West, given that the home was sold in April of that year. All right, so let me try to write this down carefully. They want me to know what's the probability that in the year ending April 30, it took place in the West, given that the home was sold during April. All right, well, I know I can use the formula that says this is going to be the probability that a home was being sold in the West and in April, divided by the probability that the home was sold in April. Okay, again, I'm just plugging into this formula that says the probability of A given B is the probability of A and B divided by the probability of B. The trick, the key to this problem is clearly matching up events A and B. Well, let me go ahead and plug in. For a home to be in the West and in the month of April is this number 140,000. Right, so that is the numerator here. And what about the probability that it was sold in April? Well, here is the total sold in April, 440,000. So I can work this out on my calculator. And I think I'm ending up with 0.32. It says round your answer to 2 decimal places. So I'm going to use 0.32 for part A. All right, let's go to part B. Part B says find the probability that a home sale was in the year ending April 30th. It took place in April, given that it took place in the West. So what they're asking me here is what's the probability that it took place in April, given that it was a home sale that took place in the West? All right, so I'm going to write this. This is going to be the probability that it was in April and in the West divided by the probability that it was in the West. All right, well, let me go up and grab my numbers. Well, this is going to be 140,000 again. But this denominator is the probability that the home was sold in the West. Now, notice this given doesn't say anything about the month of April. So really, that's going to be the total number of homes that were sold in the West, which is 1.3 million. If I work this out on my calculator, I'm getting the answer 0.11 rounded to 2 decimal places. So again, for this example, I'm using this formula. I just had to very carefully read what events were A and B in each one of the two parts of this question. All right, let's look at a couple more maybe. I'm going to look and see what might be different. Let's see. Number 19 is another question. I think number 19 is straightforward because number 19 is saying, what's the probability of A and B? But they're telling me the events are independent. So remember, the formula we use here is just probability of A times probability of B. That's just 0.1 times 0.1. So that's going to be 0.01 for that one. Okay, let's go ahead and do a couple more. I think we did number similar to 20 already. Let me stop here for number 20. Number 20 is a little different. So let's see if we can figure out number 20. All right, well, if I can fill in the diagram, I should be able to take care of part 2. So I'm going to fill in step 1, then step 2 is similar to what we talked about earlier. Well, I remember at each of these branches, the probabilities have to add up to 1. So this is 0.2, that's 0.1, that's 0.3 altogether. That would mean this probability has to be 0.7. All right, so I have that filled in, 0.7 there. Let me come up to this very top box. Again, these two probabilities have to add up to 1 here in this red box. I'm going to make this a 0.5. These two probabilities have to add up to 1 in this green box. So I'm going to make this a 0.4. All right, let me come down to this blue box. Here is a little bit of a tricky proposition because none of the boxes are filled in. But what they're telling me is the probability of I and C is 0.414. So let me call this X as an unknown quantity. Well, I know that 0.14 would have to equal the multiplications along this branch. So if I come this way and then go that way, that's 0.7 times X. But that has to equal 0.14 that they gave. So I'm just going to divide both sides here by 0.7. And so X equals 0.2. Okay. Well, if I know the top box is 0.2, I can immediately fill in the bottom box as 0.8. Then I could go ahead and work on step 2 of the problem. All right, let's see here. What else? Let's go to number 21 here. It says again, state whether these events are independent, mutually exclusive, or neither. And it says your first coin flip results in heads, your second coin flip results in heads. Well, I got to ask myself, are these independent? So what I'm asking myself is, does the result from the second coin flip affect the result from the first coin flip in any way? Well, the answer is no, right? These coin flips are totally independent from each other. You know, the coin has no memory. So what happens on the second coin flip is totally independent from what happened on the first coin flip. So these events are independent. All right, folks, hope this is helpful as you're working in the Module 10 homework.